is again another short chapter. Combinatorics 2 today, 3 on Monday, and that's it. Combinatorics 4 is the practice test, so you have a quiz on next Tuesday. The test is next Friday already. And then, yes, we're going to have one more quiz before we go on spring break. All right, do we have any questions on combinatorics 1? Because what's going to happen on the quiz, I actually wrote it already. There's 10 problems, 5 from 1 and 5 from 2. So 5 combination problems and 5 permutation problems. That's what it's going to be. So it's just going to be like this, same thing. Change the numbers. So like number 7, how many 5-digit whole numbers contain at least 1 3? So if you can do that problem, you should be able to do how many 4-digit whole numbers contain at least 1 6, right? So yeah, just make sure you can do these these problems, yeah? Any questions? No question? Pas question? Il y a beaucoup à faire, mais mon compte je le fais. All right, then we do combinations today. Let me see what we got to do. Oh, these are good problems. So a combination is when the order is not important. Because the definition of a combination is it's a collection of objects. Whereas a permutation is an arrangement of objects. Okay, so the combination of n things taken r at a time, I think your calculator does it like this. Did you guys ever look for these buttons on your calculator? I think it's in the probability menu. That's my guess. Or, this is the way I taught you when we did the binomial theorem in the first or second quarter. Remember that? N choose r all means the same thing. The combination of n things taken r at a time. And here is the formula. N factorial over r factorial, n minus r factorial. So I think we better review, because do you guys remember the fast way to compute combinations? Or is that gone from the memory? In fact, in BC Calculus next year, you have to be really good at working with factorials. Even though there won't be any permutation or combination problems, you got to be good at working with factorials. So let's do an example. Suppose you have 10 people: Alfredo, Bernardo, Carlos, Diego, Eduardo, Fuego, Guapo, Hidalgo, Iguana, and Jose. Okay? I want to select 4 of them to be on a committee. So when you hear the word committee, the order doesn't matter, right? It doesn't matter who's on the committee first, second, third, or fourth. You just want a committee of 4 people. Therefore, that's the combination. The 2 most common combinations are committees and cards. If you look at tonight's homework, look at number 2. It's just all cards. And number 1 is just committees. See? So out of these 10 people, how many ways can I select 4 of them to be on a committee? Well, the answer would be 10 choose 4. And it doesn't matter how you write it. I like to use this notation because we already used it already. And you guys remember the shortcut, or do we have to do it the long way? Okay, we do it the long way. Okay. Following the formula, 10 factorial over 4 factorial, and then 10 minus 4 is 6 factorial. Let me know when the shortcut comes back into your brain. What does 10 factorial mean? And by the way, what if it was like 57 factorial? You gonna do this? Really? You gonna write 57 all the way to 1? You're crazy, man. And then 4, 3, 2, 1, 6, 5, 4, 3, 2, 1. Hey, Mr. Park, these cancel out. Yes, they always do. So what's left? That's the shortcut right there. Remember it? So what the shortcut is, you take this bottom number, you write that number factorial, 4, 3, 2, 1, and then starting from 10, if you have 4 numbers on the bottom, you just make sure there's 4 numbers on the top, 10, 9, 8, 7. That's the shortcut. That's because everything else is going to cancel out. And then now, let the canceling begin. 4 times 2 is 8. 3 goes into 9 3 times, so 21 times 10 is 210. So if you have 10 people and you're going to select 4 of them to be on a committee, there's 210 different committees that you can make. Easy. It's quite easy. But of course, we're not going to get a problem that simple on a quiz. It'll be something like this. Suppose you have, what do you have on tonight somewhere? 5 boys and 5 girls and 4 boys. Okay, let's say you have 6 girls. Alpha, Beta, Carly, Denise, Edwina, and Fiona. And you have 5 boys. Gilbert, Hidalgo, Iguana, John, and Corn. I think there was a corn in my class last year. Is there? Yeah, okay, anyway. So, there's 11 total people, wait, 6 and 5, that's right. And got 6 girls and 5 boys. How many 5-person committees can I make? So already, committee. You see the word committee? I'm gonna make a 5-person committee. Well, let's just do that. How many 5-person committees can you make? No restrictions. How many total people are there? 11. How many do I want to select? So 11 choose 5. You write that formula down, you're gonna get 3 out of 4 points. You want the 4th point? You gotta compute the number. So what's the best way to do it? Use the shortcut. You take the smaller number, 5, 4, 3, 2, 1, and then 11, 10, 9, 8, 7. And let the canceling begin. What do you want to do? 4 times 2 is 8. 3 goes into 9 3 times. 5 goes into 10 2 times. So all you have is 42 times 11. Okay, let's just do it the long way. 2, 4, 2, 4, 462. 462 different committees. Okay, well, I'm not going to do any more computation. That's up to you already. Yeah, you got to practice the computation. Okay, but let's put some restrictions on it. How many 5-person committees contain 3 girls and 2 boys? Okay, well, how many girls do I have to choose from? 6. How many ways can I select 3 of them? 6 choose 3. Now there are 5 boys. How many ways can I select 2 of them? 5 choose 2. Now, what do I do with these 2 numbers? Do I multiply them or add them? Well, you got to ask yourself, are they on the committee at the same time? Or these are mutually exclusive cases? No, they're on the committee at the same time, so you multiply. Anyway, I told you, the word and means multiply. Here, and means multiply, or means add. It's very simple. Mr. Park, even that's too easy for a quiz question. You're right. So how do I kick it up a notch? How many 5-person committees contain at least 3 girls? What does at least 3 girls, why would we want at least 3 girls on the committee? So things get done, right? Because if we don't have at least 3 girls, you know what's going to happen. Not much is going to get done. Okay, so what does at least 3 girls mean? 3, 4, or 5 girls need to be on the committee. But now you got to ask yourself, is it better to compute it directly like that, or should I do the complement? What is the complement of at least 3 girls? 2 girls or less. So what would be the complement? 2 girls, 1 girl, or no girls. And then subtract that from the total. So is it better to compute it directly or do the complement subtract from the total? Really? Compute it directly because that's just 3 computations. The other one is 4 computations. You got to go 2, 1, or 0, and then you got to subtract it from the total. A lot of chances to make a mistake there. So this one, I think we should do it directly. So we break it up into the 3 mutually exclusive cases. You can have 3 girls. You can have 4 girls. Hope this is catching on the video. And then 5 girls. Try to squeeze it in there. So how many committees have 3 girls? Well, we just did it right here. It's 6 choose 3 times 5 choose 2. Because if 3 of them are girls, that means the other 2 are boys, right? What about 4 girls? 6 choose 4, and then you need 1 boy then. 5 choose 1. And then what about 5 girls? 6 choose 5, and that means no boys. 5 choose 0. That would be the most efficient committee then, yeah? Mr. Park, that's insulting. And then what do I do with these numbers? You multiply these because they're occurring together, right? And then what do I do with these numbers? You add because these are mutually exclusive cases. So you write down that formula, you'll get 3 out of 4 points. You want the other point and you gotta compute it. Okay, let's practice. Let's see if we can do this in our head. 6 choose 3, so in your brain you go 6, 5, 4 over 3, 2, 1. The 6's cancel out and you get 20. See, you guys can do it. If not, just write it out. 5 choose 2. 5 times 4 over 2 times 1. See, you can do it. 6 choose 4 is the same thing as 6 choose 2. Remember that? Why is 6 choose 4? I showed you this when we did the binomial theorem. Again, why is 6 choose 4 the same as 6 choose 2? Remember? Come on, somebody gotta remember something.
The formula.
Yeah, the formula, but then remember what I said? No. Okay, using the formula, how do you compute this? 6 factorial over 4 factorial, 6 minus 4 is 2, right? How do you compute this? 6 factorial over 2 factorial, 6 minus 2 is 4. Why are these equal? No, duh! It's duh! You guys don't remember that? I remember it. Duh! Okay, so 6 choose 4 is the same thing as 6 choose 2. Why is it better to have a smaller number on the bottom? Okay, here, let me show you. 6 choose 4, if you're going to use the shortcut, it's going to be 4, 3, 2, 1. 6, 5, 4, 3. 6 choose 2, you only have 2 numbers on the bottom. Which of these would you rather compute? Duh! Okay, 6 choose 4 is the same thing as 6 choose 2, so 6 times 5 over 2 times 1. Anything choose 1 is anything. 6 choose 5 is the same thing as 6 choose 1, which is, and anything choose 0 is 1, right? Or do we need to draw it on this side? Okay. And then can I assume we can compute these numbers? I don't trust you. 200 plus 75 plus 6 is 281. Dang. Alright, so yeah, community problems are easy, just gotta read. Okay, card problems. Every year students have trouble with card problems. Now, in order to do card problems, can I assume that everybody knows what a deck of cards is? You don't know what's in a deck of cards? Okay, I have to explain that. So there's 52 cards in a deck. 13 of them are hearts. 13 of them are spades. 13 of them are clubs. And 13 are diamonds. Okay? In each, we call these suits. These are the 4 suits. In each suit, the 13 cards are, we got ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, and 2. So each of these has these cards in it. That's what makes it the 52 card. Okay, do you guys know what a face card is? A face card, because it comes up on the homework. A face card is a card that has a face on it. But then if you never played cards before, you wouldn't know. So these are the face cards. The Because if you ever play cards, that's the one that have faces. So how many face cards are in the deck? Yeah, I've got 4 plus 4 plus 4, which is 12, yeah? Because remember, there's a king of hearts, a king of spades, a king of clubs, and a king of diamonds. There's a queen of hearts, queen of spades, queen of clubs, queen of diamonds. So each one of these has each of the 4 suits. 13 times 4 is 52. That's how you get the 52 cards. All right, so what kind of questions am I going to ask? Well, it says from a standard deck of cards, 5 cards are dealt. Well, how many different ways can you get a 5-card hand? This is actually how you compute probability of playing poker. Those of you who know cards, you guys know poker? I just don't know. Okay, so you have a deck of 52 cards. How many ways can I just select 5 of them to be in my hand? 52, choose 5. Okay, I will leave the computation to you. Actually, I wouldn't give this because the answer comes out more than 1 million. The answer is 2,598,960. So like I said, on my quizzes and tests, all the answers are less than 1 million. So what can I do to make this number smaller? Make it a 4-card hand then, right? Or a 3-card hand. That way the numbers are going to be smaller. Okay, but like we're doing 5, so if you want to use your calculator for these, you can. If you want to. Okay, so, well, I don't want to do all of these. You guys need to do it. So you know what? Let's do poker hands, because poker hands are harder to. If you can understand how to do poker hands, then these easy ones over here are easy. Okay, you know what the hardest hand to come? Well, first of all, do you guys understand poker? Some of you do, some of you don't. What's the, without any wild cards, what's the highest poker hand you can have? A royal flush. Now some of you are going to say, what? A royal what? Don't worry, I'm going to define it so that you don't have to memorize these. A royal flush means you have ace, king, queen, jack, 10, all of the same suit. So like ace, king, queen, jack, 10, all spades, all hearts, all clubs, all diamonds. How many different royal flushes are there? 4. I just told them to you, right? Ace, king, queen, jack, 10, spades, hearts, diamonds, clubs. That's it. 4 royal flushes. So, next chapter we're going to do probability. If I just were to deal randomly a 5-card hand, what's the probability of getting a royal flush? 4 out of this. So that's why you have to know combinatorics before you can do probability. The only difference is the probability just has a denominator. That's the only difference. But you still have to count both of them. You got to count the numerator and the denominator. Okay, what's the next highest hand? Those of you who know poker.
Full house.
Is it full house? Or is it straight flush? Or is it 4 of a kind? 4 of a kind? Okay, let's do that. 4 of a kind. Now the thing is, the ones that are on the top, the highest ranking ones, they're kind of easier to compute, and then as you go down, they get harder and harder to compute. Okay, so when you do poker hands, just like we do permutations, do a specific case, and then multiply it by the number of cases. Okay, so 4 of a kind. Let's do a specific case. How about 4 aces then? Okay, just do 4 aces. How many aces are in the deck? 4. How many ways can I select 4 of them to be in my hand? 4, choose 4, which is 1, right? Because that's the same thing as 4, choose 0. And then now the 5th card has to be something that's not an ace. How many cards in the deck are not aces? 48. How many ways can I select one of them to be the 5th card? Because it's a 5-card hand. It's like making a committee, right? You have 4 and then 1. So wouldn't that be 48, choose 1? Okay, so that's how many ways I can get 4 aces. Or you can go like this. Well, I could get the 4 aces with the 2 of clubs, the 4 aces with the 3 of clubs, the 4 aces with the 4 of clubs, and so forth. You'll get the same number. So this is how many ways you get a 4 aces? What about 4 of anything though? What about 4 kings, 4 queens, 4 jacks, and so forth? So now you need to multiply it by the number of cases. 13. Because there's 13 of these. We'll call these values. Okay, what do we call these? Values. There's 13 values, right? This is how many aces. Then you could kings, queens, jacks, and so forth. That's why you times it by 13. So you do a specific case multiplied by the number of cases. What does that come out to? I'm afraid to even ask. That's 1, that's 48, that's 13. So basically 48 times 13. 4 carried 2, 8, and 4. So that's 4, 2, 1, 624. And you know how you rank your hands? The lower the probability, the higher the rank. That's how you use. So if you don't know what the order is, figure out the probability, and then the lowest probability is the highest rank you can. Okay, I'm not going to do all of them. Okay, what do you want to do? What do you think the next highest ranking hand is? Straight plus? Or is it a full house?
Straight flush.
Straight flush? Okay. Now, what is, or just a regular flush? Now, those of you who know how to play cards, straight flush. What the heck is a flush? A flush means all the cards are the same suit. So you have 5 cards that are all hearts. 5 cards that are all diamonds. That's what a flush is. A straight flush would be 5 cards, all of the same suit, but they have to be in order like this. 5, 6, 7, 8, 9, all hearts. You guys know what I mean? Or 3, 4, 5, 6, 7, all spades. That's what a straight flush is. So how many straight flushes are there?
Okay.
Well, let's just count one case. Just do diamonds. Okay, first of all, would a straight consist of, can you use the ace as a 1? Oh, I think you can. Well, it just depends. You decide when you're playing poker. Can we count the ace as a 1? Most times it would be yes. So if you can count the ace as a 1, how many different straights are there? Here's go like this. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9. How come I don't count this one?
There's 1.
Because that's a royal flush. We already counted it already. Right? So there's only 9 of them. So just doing one, like spades, there's 9 of them. What about hearts? There's 9 of them. What about diamonds? 9 of them. What about clubs? 9. So what is that? Really? 9 plus 9 plus 9 plus 9? I'll give you a hint. 9 times 4. 36. Which means this is higher than 4 of a kind then, because it's harder to get. Because there's only 36 ways. The probability is smaller. You see? So this one should be above 4 of a kind. Okay, what do you think the next one is?
Full.
Okay, full house, I'll tell you right now. No, you know what? We're going to do it. Full house. Well, see if you can understand this, because like I said, if you can understand what I'm doing here, then these problems are tame compared to this. Okay, so first of all, what is a full house? Full house means you have 3 of something and 2 of something else. So like you could have 3 kings and 2 eights. You could have 3 jacks and 2 threes. You get it? 3 eights and 2 sevens. 3 of one kind and 2 of another. Okay, so let's do a specific case. What do you want to do? 3 aces and 2 kings then? Okay, how many aces are there in the deck? 4. How many ways can I select 3 of them to be in my hand? 4, choose 3. How many kings are in the deck? 4. How many ways can I select 2 of them to be in my hand? 4, choose 2. So that's how many ways I can get 3 aces and 2 kings. But now here's the hard part. Now you gotta multiply by the number of cases. Okay, so this is aces and kings. What about aces and queens? What about aces and jacks? What about queens and eights, jacks and 4s, 10s and 8s, 9s and 2s? Get rid of that ace on the bottom. So what is it? Come on, we just learned it. Out of these 13 values, how many ways can I select 2 of them to be like aces and kings? I just told you the answer. Out of these 13 values, how many ways can I select 2 of them? 13, choose 2. Or do you really want to count it like this? 1, 2, 3, 4. No, come on, that's nuts if you did it that way. 13, choose 2. Okay, is that the answer? Not quite. You know why? I would have to multiply this by 2. Somebody tell me why.
3 and 2 and 2 and 3.
Exactly. So we did 3 aces and 2 kings, but couldn't it have been switched? 2 aces and 3 kings? So that's why you have to multiply it by 2. Tricky. Anyway, out of all of these, you know which is the hardest one to compute? Nothing. To compute how many hands have absolutely nothing, you would have to count all of these and then subtract it from that. That's the only way you can get nothing. Okay, let's just do one more. I think that's good enough. Okay, how about 2 of a kind then? No. 2 pairs then. You guys know what 2 pairs is? A pair of something and a pair of something else. Like 2 jacks and 2 8s. 2 9s and 2 5s. That's why they call it 2 pair. A pair and a pair. Okay, so let's do a specific case. What do you want to do? 2 aces and 2 kings then? Well, you just pick something. It doesn't. Okay, how many? Okay, so we're doing 2 pairs. This is the last one we're doing. How many aces are in the deck? How many ways can I select 2 of them to be in my hand? 4, choose 2. How many kings are in the deck? 4. How many ways can I select 2 of them to be in my hand? 4, choose 2. Okay, now the 5th card cannot be an ace or a king. How come? Because otherwise it would be a full house, right? Okay, so how many cards in the deck are not aces or kings? 44. How many ways can I select one of those to be the 5th card? 44, choose 1. Because you gotta select 5 cards. 2 aces, 2 kings, and 1 card that's not an ace or a king. Okay, so this is how many ways you can get a pair of aces and a pair of kings. Now, you know what, last year, now I remember last year, they said, well, can't you get 4 aces? Isn't that like 2 pairs? Is 4 aces the same thing as 2? Are 4 aces the same thing as 2 pairs? No! Anyway, if you play poker and you get 4 aces, you can say, oh, I got 2 pairs. That's way down on the list. 4 of a kind is up here on the list. No, it's not. Okay, so anyway, this is how many ways I can get 2 aces and 2 kings. Now I need to multiply by the number of cases. Come on, we just did it. Okay, got aces and kings, but can also have aces and 9s. What about kings and 6s, jacks and 3s, 10s and 9s, 8s and 2s? How many ways can I select 2 of them? 13, choose 2. That's the number of cases. 13, choose 2. You see, you gotta get the hang of this. This is not easy. Don't worry, I'm not gonna give you like poker hands, okay? I'm not. Because some people don't know poker hands. So I'll describe it like that. See, like that. At least 1 face card. Or at least 3 face cards. So it'll be like that. And it'll probably be a 3 or a 4 card hand because otherwise the numbers get too big. Okay, what time is it? Okay, a couple more examples. Okay, I want to do the distribution problem. Okay, this is a very famous problem in combinatorics. Okay, so tonight's homework, you got the 3 Stooges. Can you think of a group that has 4 people? The Beatles, okay? What is 2 plus 3 plus 4 plus 5? 14, am I right? Okay, suppose there's 14 different candy bars on the kitchen counter, candy bars. How many ways can I distribute them to 4 people? Who are the 4 people? John, Paul, George, and Ringo. You guys know the Beatles? Well, those are the beetles right there. How many ways can I distribute these 14 candy bars to the 4 beetles if John's gonna take 5, Paul's gonna take 4, George takes 3, and Ringo takes 2? How many ways can the candy bars be distributed? Okay, this is a combination problem. This is called the distribution problem. You're gonna get it right there. I forget what number that is, number 5. Except that one looks easier than this one. Now, since this is a combination, it doesn't matter who goes first. Who do you want to go first? John. Okay. There's 14 candy bars on the kitchen counter. John comes in. How many ways can he grab 4 of them to put in his lunchbox? Really? 14, choose 5. How many candy bars are left? 9. Okay, there's 9 candy bars left. Who's going next? Okay, Paul. Paul walks in. He sees 9 candy bars. How many ways can he select 4? 9, choose 4. And it doesn't matter who goes first, second, third, or fourth. That's why it's a combination. How many candy bars are left on the counter? There's 5 candy bars left. Who goes next? George? Okay, George, how many ways can you take 3 of them out of the 5? 5, choose 3. And then finally, there's only 2 candy bars left. How many ways can Ringo take them? 2, choose 2, which of course is 1. Okay, well let's compute this because there's something neat about this computation right here. How do you compute 14, choose 5? What's the formula? 14 factorial over 5 factorial. 14 minus 5 is 9 factorial, right? How do you compute 9, choose 4? 9 factorial over, really? 4 factorial, 5 factorial. What about 5, choose 3? 5 factorial over 3 factorial, 2 factorial, that's 1. Hey, Mr. Park, things cancel out though. This 9 factorial cancels this 5 factorial cancels that. What's left? This is what's left. Does that look, what do these numbers have to do with the problem? There are 14 candy bars. John will take 5, Paul will take 4, George takes 3, Ringo takes 2. So if you remember this can save you time. But it's up to you. And when we do these problems, there's so many, there's the cabin problem over there. You know what? What time is it? I think we should do the cabin problem. Okay, this is the last example. Okay, let's just do 2 cabins instead of 3 cabins. Okay, so this is called the cabin problem. Okay, cabin A holds how many people? Let's say 7. Cabin B holds 6 people. Okay? So there's 13 people. Now tonight you got Bert and Ernie. Okay? Let's go 3 people then. Who are the 3 stooges? Larry, Moe, and Curly. Yeah? If you know the 3 stooges. Okay? It doesn't matter who they are. Okay, so how many ways can I not arrange but put these 13 people into these 2 cabins if the 3 stooges, Larry, Moe, and Curly, have to be together? Okay, you guys understand that? Larry, Moe, and Curly have to be in the same cabin together. So aren't there 2 cases? Either Larry, Moe, and Curly are in cabin A or they're in cabin B, right? So what if Larry, Moe, and Curly are in A and then Larry, Moe, and Curly are in B? These are our 2 cases. Okay, so if Larry, Moe, and Curly are in cabin A, that means these 3 people already took up 3 of the spaces. How many more people do I need to select? I need to select 4 more because the cabin only holds 7. Everybody understand? Okay, so out of the 13 people, if I take away Larry, Moe, and Curly, there's only 10 people left to choose from, right? So out of those 10 people left over, how many ways can I select 4 more to go into cabin A? 10, choose 4. Now, it doesn't matter which cabin you fill up first because this is a combination. The order doesn't matter. There's 6 people left. How many ways can I select 6 of them to go into cabin B? 6, choose 6. Which of course is just 1, yeah? Okay, now let's do the second case. What if Larry, Moe, and Curly Larry, Moore, and Curly are already in cabin B, that means I have to select 3 more people then, right? So out of the remaining 10 people, how many ways can I select 3 of them? 10 choose 3. Now there's only 7 people left. How many ways can I select 7 of them to go into A? 7 choose 7, which is 1. That's your formula. And how come I add them? Because these are mutually exclusive cases. This is called the cabin problem. And then I'm not going to go over this, but number 8, that's called the no, maybe we shouldn't even give it a name. And if you think there was a lot of names for this one, wait till we get to like the next one, the next lesson on Monday. Oh,